The definitions of accuracy and precision. Accuracy, how well a measured value agrees with an accepted value or the correct value. Accuracy indicates how good or correct a measurement is. Precision, on the other hand, is how close a measurement is to the other measurements in the data set. Precision is an indication of reproducibility. Now, you can have accuracy without having precision, and precision without having accuracy. Our goal is to have both accuracy and precision in all of our measurements. So let's see visually the difference between accuracy and precision in a series of measurements. So in our case here, our accepted value is going to be the bullseye in the middle of the target, right? All the other black dots around that are our measurements compared to the accepted value, which is the middle of the target here. So in the first case, we can see that all of our measurements here are, except for one, which is in the bullseye target, are far away from the accepted value. So we're going to say that we have low accuracy. And also the measurements are all far away from each other, right? You see here, this measurement here is very far from this one, very far from this one, again here, here. So we're going to also say have low precision. In this case here, we have, here's our accepted value, or what we're trying to achieve, and all of the values that we've measured here are going to be very far away. So again, we have low accuracy. However, all the measurements now are very close to each other, and so therefore we're going to have high precision. And in this case here, if our accepted value is the red dot, we have 4 out of the 7 measurements are inside or on the red dot. So you would say that this has some high degree of accuracy. Even the ones that are not on the red dot are pretty close to the red dot. So we would say that if you took the mean of all these dots, you would probably have a very high accurate measurement. And now, as far as precision, they're close together, but not as close together as we want for like this one here. They're better than this one here, but they're still fairly scattered. So we're going to say we have low precision. And in the final case is we have both precision and accuracy. We're inside the red dot, and they're all the measurements are very close to each other. We need a means of determining accuracy and precision, a mathematical or numerical means of doing that. We just can't look at something and eyeball it. So we need to have some type of numerical measurement that tells us whether or not we are accurate and or precise. So for accuracy for a set of measurements, we are going to determine that the average or the mean of the set of measurements and their percent error compared to the actual value or the expected value is going to be our determination for accuracy. Now, when determining whether or not a set of measurements is accurate or not, we're looking for the smallest percent error that we can do. The smaller the percent error, the more accurate a set of measurements is. Now, looking at precision. Precision is, remember, the closeness of the measurements to each other, right? So we're looking at, there's 2 ways to look at this. One is a more crude way than the other, and that is the range. And then the better way is the standard deviation. Now, I don't expect the high school student to understand or be exposed to the standard deviation yet. Some may have in another course where they were looking at statistics or something like that, like a math course or maybe even an intro business course. But the bottom line is, what you're looking for here for precision is the smallest amount of scatter in your data. And the range will give you a crude way to look at that, whereas the standard deviation is the better way to do that. So let's look at how these are applied in the next page. Okay, so let's see how the standard deviation measurement relates to precision. Now, again, I'm not going to require you to understand what standard deviation is for the rest of the class. What I do want to do is just expose it to you to show you what it means when you see data sets that would have narrow and broad peaks, and that indicates by looking at it in precision and imprecision. So let's say, for example, you wanted to plot all of your values that you did versus the frequency of the value, right? So on this axis here, that doesn't show, but that would be the number of responses. And when you plot your data, the more responses you get closer to the measured mean, the tighter the distribution is going to be, right? So let's say you measured the density of aluminum sample in the lab using a technique, and you did it several times. Let's say you did it 10 times, and all the values were in between, let's say 2.67 and 2.72. So that the distribution is fairly tight along that. And if you took the mean of your measurements and compared it to the real value, or the 2.69, you would see that your mean is pretty much the same number as the accepted value, and therefore you would say your data is accurate and your data is precise because it's very grouped very tightly. So a small standard deviation, as down here, means precise measurements. You have a very sharp and narrow peak. A large standard deviation means that you have a broad and diffuse peak, not very sharp. So your measurements are much more spread out. So you would have imprecise measurements. So in this case, we have both precision and accuracy. In this case, we have a measured mean value of your data set to be off from the real value. It could also be off on this side here. But so now your error would tell you this value here. So let's say this error is 2%. But you do have data that's real well clustered together. Think back to the target, where the target, all the data was off to the skew, but we did have it very tightly packed. So in this case, we have inaccuracy, but we have a very precise distribution. Now in this case here, we have a more spread distribution of our data, but when we take the mean of the data, we get a number that's exactly or very close to the real value. So our error is very low, but our spread is very high. Therefore, we have accurate data, but it's very imprecise. And then the last case here is we have both inaccurate data because our mean value of our measurements and our real value are way off, have a high error value, and we have a very broad peak. So inaccurate, imprecise, inaccurate but precise, accurate but imprecise, and accurate and precise. We need a technique or a procedure for determining whether or not our data is accurate. And so we're going to use this concept called error. And there are two errors that we're going to report. One error we can say is just the difference between the experimental value and our accepted value, and that's just going to be a raw number. And then we're going to look at percent error. It's a numerical way of expressing how accurate a value is with respect to the accepted value. And the percent error is the better term to use because the percent error looks at the error relative to the accepted value. It gives you basically a relative amount. All right. So, for example, if you had a 0.1 gram error in a sample that is 1 gram versus a 0.1 gram sample, 0.1 gram error in a sample that's 1,000 grams, you can see that the 0.1 grams in 1,000 grams is probably a lower percentage error than it is in 0.1 gram in a 1 gram. So the percent error is the better term to use, the better methodology for reporting error, because it's a relative weight against the size of the accepted value. So here's the formula for that. Percent error is the absolute value of the experimental value minus the accepted value divided by the accepted value times 100%. And our goal is for accuracy is to have the lowest percent error possible. So a lower percent error means a higher accuracy in a measurement. All right. So the other thing too is I want you to do now is to stop the video and copy this equation down, because you're going to be using it in the next part of the video. So stop the video, copy this equation down, and then when you're ready to go on the video again, hit play. Stop it now. Okay, so what I want you to do now is to use that equation that you just copied and calculate the percent error for these measured values right here, right? And for your accepted or actual value, or the correct value, you're going to use 2.69 grams per cubic centimeter. These are all in grams per cubic centimeter. So using the data that we have here, you're going to then, and this value, you're going to calculate the percent error and put that value in this column here. So what I'd like you to do now is to stop the video, copy all this information down, do the calculation, and then hit start when you're ready to come back to the video. So stop the video now. Okay, so you've done the calculation and you should have gotten these values here. Based on this particular formula that I've told you to copy down, this value for your accepted value, and these are your measured values. So if you got those numbers, congratulations. It looks like you understand how to calculate the percent error. If you struggled a little bit, you should make sure that you copy the equation down or you did your math right. Don't forget this is the absolute value, so you should have no negative percent errors, right? It should always be positive. So once you have calculated the percent error for a set of data or a set of measurements, the next question to ask is, well, now what do I do with that, and what percent error is acceptable for data to being accurate, and what percent error means that I have data that is inaccurate? And the answer to that question is there's no right answer or there's no wrong answer. It depends on the type of process you have and how much error you can tolerate in your process. So let's look at two examples here to kind of illustrate that. When you fly in an airplane, the goal is to get from point A to point B, and when you take off and land, to do safely without crashing. So let's say that with the data we have, you have a 1% chance of crashing every time you take off on an airplane. Well, you could say, well, that's quite high because I fly more than 100 times a year, and therefore that's pretty much guaranteed. Not always, but that's pretty much guaranteed at some point in my life I'm going to crash in an airplane, and that may kill me. And therefore, so that 1% is really too high for that particular application. Now let's say you're a baseball pitcher and your goal is to throw strikes. But we all know that baseball pitchers can't throw perfect strikes all the time. So let's say that you're a really good baseball pitcher and you throw 90% of your pitches in the strike zone on a consistent basis. So therefore you have a 10% error. Well, in that case, the 10% error is going to be tolerable because most people can't throw a baseball in a strike zone on a consistent basis 90% of the time, even the pro pitchers. So it's all dependent on what application you have and how much error you can tolerate and still get an acceptable response. But for chemistry, we're going to set an arbitrary value for moving forward. So from now on, if a set of measurements or a set of data has an error of greater than 0.1%, we're going to say that data is suspect as far as accuracy. Anything that's 0.1% and lower, we're going to say that data is always going to be accurate. Not always the case, but for the most part, that'll be what we're going to stick with for moving forward. Okay, in this slide, I've tried to wrap up or bring all together the concepts that we've learned about. We've learned about accuracy, we've learned about precision, and we learned about error. And we've learned about ways to use the data and those types of measurements, percent error, range, to determine whether or not a set of measurement data is accurate and or precise. So once you do all the math here, and I've taken the average here of all the data for each column, for each person, and then I've calculated the percent error, and I've calculated the range for the data set. Let's just quickly go through this. So by looking at this, you can say, remember we talked about the error before, Anything that's greater than 0.1% is going to be suspect as far as accuracy. And so here we have 0.17%, that's higher than 0.1%. Our mean for that particular data, Lisa's data, is not close to the accepted value. So Lisa's data is neither accurate, it's not accurate at all. Her data is also not precise because she has a pretty wide range in values, 0.18 grams, which means that in the 4 samples that she's given, 2 of them vary at least by almost a gram, which is quite high for that. So we're going to say that Lisa is both inaccurate and imprecise. Lamont, on the other hand, has its mean of his data is exactly the same as the accepted mass, so he is accurate. Our percent error tells us that. And his range is quite low, 0.06 grams. And 0.06 grams, based out of 47.42 grams, is quite tight as far as data. And therefore, we're going to say that Lamont is accurate and precise. And finally, our last candidate is Lee. Lee's mean of his data set is much higher than the accepted mass, 47.92. So his error is 1.05%, considerably higher than the 0.1% that we've touted as being the boundary between data that is suspect as far as accuracy and accurate data. But his data has a very tight distribution. So the range between the high and the low is only 0.06 grams, which means the other 2 samples have to be also within that range. And so therefore we're going to say that Lee, because of his error is very high, is inaccurate, but because his data seems to be very tight as far as a small range, we're going to say it's precise. So if you didn't get the same analysis by that, you should go back and kind of review what we just did. But if you're on board with that, then congratulations. I think you understand this a little bit better. And let's do some practice data on the next slides. So our last task in this video tutorial is for you to now bring together all that you've learned in the last 15 minutes and now apply that and finish this table here and determine which of the scientists has the most accurate and precise data. And it's based on a process where we're going to be synthesizing ammonia during a chemical reaction, and then we've measured the ammonia made, and we're going to compare that to what we expect is the accepted or correct value. Our correct value for this process is 56 grams, and then these are the data measurements that we've made for each individual scientist. We've run the experiment 5 times for each scientist, so it's your job now is to fill in the mean for each set of data, calculate the error and calculate the range, and then predict which one is both which one is accurate, which one is precise, and if it's both, which one are precise and both accurate. So your goal now is to stop the video, copy all this information down, work the answers, and then when you're ready, start the video again. So stop the video now. Okay, so here are the answers based on the information I provided to you in the previous slide. When you did the mean or the average of all the data sets, you should have got these values here for each data set. So Dr. Hurley's has 56.02 grams, Dr. Bunsen Huntington's 54.89, and Beaker's 55.99. Right? Then you would have calculated the error, and then you would have calculated the range. And based on these sets of data for each one, you're going to make predictions on whether or not each scientist was accurate and or precise when they did their measurements and reactions. So looking at this, we already told you that when the percent error is lower than 0.1, you're going to have accurate data, and since the value here, 56.02, is only 2/100ths of a gram away from the accepted value, and the error is much lower than 0.1, that's going to be accurate data. So Dr. Hurley is accurate. Now look at the range here. The range here is quite high, 0.65, and so we're going to say that that is not precise. Dr. Bunsen-Honeydew, the error here for based on the mean compared to the accepted value is 2%. We already know that that's much greater than 0.1%. So that means that Dr. Bunsen-Honeydew is not accurate. However, his range of his data is quite narrow, 0.07 grams, and therefore he is precise. And then Beaker has not only a very low error and a mean that's very close to the accepted value, but his range is also quite low too, and therefore Beaker is both precise and accurate. So if you didn't get those answers and couldn't follow the analysis, you should go back and review the slides. But that is it for this particular tutorial, and you should now have a better understanding of accuracy, precision, and how to determine the accuracy and precision of a set of data.